So, hello everyone. My name is zkahraman. I am going to be presenting Multi-AUV mission planning and execution, which is my project under SMaRC. So, starting with an overview, I will first explain why this is a good idea to do, and I will then go into what I have actually done and what am I doing nowadays. And then we will have questions afterwards if you like. You can stop me at any time to ask if you have anything to ask. First, starting with the big picture. Simply, if the simplest way, some missions are just not impossible, are just not possible with one agent. Caging, capture, defense, these kinds of missions require being at multiple locations at the same time, which is obviously not possible with only one robot. So these are like natural types of missions where multi-agent systems are required, not just good to have. Then there are missions where, one AUV can accomplish, like if you want to make a map, if you need to cover some area, you can do this with one AUV. The problem is the oceans are a little large, to say the least. If to put some numbers on that, I copied from Wikipedia the area and volume of water we have on Earth. 1.3 billion cubic kilometers is a big number, to say the least. And if you do a bit of a back of the napkin calculations, we effectively need 1.8 million missions to cover the ocean area with just one AUV. That's a lot of missions. I don't think we have that much time to do this. So there's a reason. There's your other reason to actually try doing this with multiple agents. The more agents you have, you basically divide up that 1.8 million number into that many agents you have. So we need swarms. We need whole groups of AUVs covering everything. And to continue on the big picture, we cannot really do swarms with very expensive, very hard to create platforms. That's where vehicles like SAM come in. They are small, they're easy to deploy, easy to use, and they're cheaper to produce. That's why we can produce many of them, make a swarm out of them, let them be, and they can just go over the entire ocean as a group. And these are the usual operating conditions of such small vehicles. The details are not that important. I think we're all more or less familiar with these numbers already. They're just there as a reminder. So what have I been doing this past some years? Starting with, so first, we need to get one AUV to be autonomous so that we can have many of them doing a mission together. If we cannot trust one AUV, we cannot trust a group of them, even less. That's why we started with getting behavior trees into these AUVs, because we know behavior trees are composable, they're reactive, and they're easy to work with. So even a novice can actually understand what it is doing, how it is doing it, and why it is not doing what you expect it to do. So you can easily see what is going on with your vehicle. And that is paramount when your vehicles are expensive and they're cut off from you for long periods of time. You can look at the logs, see what it has done, what it has not done, and why it has not done those things, or done those things. Could be many. And I have done this with Chris, who will be presenting today as well, if I remember correctly. Moving on to more multi-agent stuff. Underwater caging and capture. As I said, caging is one of those missions where you have to have multiple vehicles. One vehicle is just not going to be enough. Why do you want a cage? Is this core of this project. We have an evader, something, someone, some entity that we want to capture. We want to create a cage around it such that it doesn't know it is being observed or it doesn't know it is being manipulated somehow, but we can move the cage around and it has to move with us. Or it has to go through us before it gets out of the cage, so we know that it is trying to escape. Additionally, we would like to know under what circumstances can we guarantee the existence of such a cage. This becomes more important on the defense side of the project, where the evader is usually a foreign submarine that is snooping around, and we don't want them to snoop around that much. So we want to know when can we cage this submarine so that we know when it is trying to go somewhere that it is not supposed to. And this is more or less how it looks like. I will quickly go through the video. Unable to play video, error 5. I don't know what that means, so let's just skip it because I have pictures of it anyways. This is what a usual mission looks like in this caging operation. There's a signal of sorts somewhere inside this initial area where it might grow with the speed of this vehicle that we think is there. So this growing area is where this evader might be at any time as a function of time, basically. And we want to create a cage with our many small submarines such that this growing area can be contained and can be stopped from being stop the growing of the area as well. We can use the land in our advantage because we know submarines usually cannot go on land. So how can we do this was the question, basically. If we do, using the method that we devised, we can find on the surface with vertical walls going down to the seabed exactly where we need to place our small detecting submarines such that we, one, minimize the number of submarines required to do this job by using as much of the land as possible to our advantage, including the depth profile of the area. So you can see on the left image, there's a large, like long island or some land that is being used as part of the cage. And then the submarines need only be deployed on the red, white striped lines. It is using the islands, it is using all the shallow areas of the water to minimize the number of total area that the submarines themselves need to cover. Similar with the three islands, but if the island or the land is far away and there are no shallow areas, then the cage is tighter around the growing uncertainty area of where the evader might be. That's what the yellow shaded areas are. To get there, we solve some problems. You can find the details or ask me about the details later if you're curious about it. These are the three main problems that are being solved to construct the problem and solve the actual problem that we're trying to solve. So that only works in 2D, basically. You have your depth map and you position your AUVs perpendicular to that wall, kind of like you see on the edges of this image here. But if you want to very tightly cage the evader, you need to make a 3D spherical cage. Why spherical? Because now you can shrink the cage until you actually capture the AU submarine or evader as well. And to do that, it is actually usually not possible to do this at the beginning of the mission. Most of the time, the uncertainty area is so large that the number of AUVs you would need to create such a spherical cage is just too big, even for militaristic purposes, that it is not feasible to do so. That's why it's better to start with these wall type cages to use as much of the land as possible to create a large but unshrinking cage. And then once you detect the evader a second time, you can move in from closer and create this smaller, more robust, let's say, spherical cage. And this is what it looks like when you create such a cage with many AUVs on the left, and the right red polyhedra shows the remaining volume once you create such a cage. That is the volume shape in which the evader is free to move inside without getting captured. And because it's spherical, it has a single center, it can be shrunk down at the same speed by all of the AUVs slowly until we don't know where the evader is in that volume, but we don't care because eventually we will have covered all of that volume by shrinking the cage. And eventually one of the AUVs will detect it directly, and then that's the capture. And clearly by capture, we don't mean like physically being able to hold on to a submarine using SAM, for example, because that's just not very feasible yet. By capture, we mean sensor detection in a direct manner, like it's in our radar, basically. And out of curiosity, basically, we want to see what kind of radiuses we can get out of these spherical cages, like, and how efficient they are. As you can see, the efficiency drops as the number of AUVs increases, or as the radius you want to create increases, you need incredibly more and more AUVs. At 99 AUVs, we get to the radius here is a normalized distance, so it's not exactly, it doesn't have a metric, but you can see the curve is getting worse and worse as you increase the radius or the number of AUVs. That's why we need the wall types to get there first, so that we don't need a large radius. We can just do well with a small radius with few AUVs. So the main guarantee out of that is that the evader cannot escape either cage. That's the guarantee that we wanted. That's the guarantee we have. Given the initial state of the world and the known parameters of these evaders and our own AUVs and where they start and so on, we can guarantee this caging, either at the large cage level or at the spherical cage level, depending on numbers. Spherical cage may not be possible, but at least you have the large cage. At least you know some area where the evader cannot escape from. And as a secondary result, we know the circumstances in which we can create such cages, like what kind of speeds we need for the evader, what kind of speeds we need for the AUVs, how many AUVs we have, do we have enough, how far away they are. Like we have parameterized basically the whole thing, saying if these are the parameters we have, you can guarantee caging. If this is too large or this is too small, you cannot guarantee a cage. You can attempt, but there's no guarantee. Then after realizing that having a lot of AUVs very close by acting together requires them to be safe in such circumstances while still getting their mission done. And that's where we have combined control barrier functions, which are very heavily control theory liked methods to guarantee safety under known dynamics. And behavior trees, which we have already used, so that we can switch between different behaviors to still guarantee that the mission will be complete while still being as safe as possible. So that's the goal here, to guarantee that the mission will be done while trying to keep every constraint we have satisfied, which is harder than it looks, because how many constraints are you going to satisfy? Which ones are you going to satisfy? What is the order in which you are okay with not satisfying? For example, collision is number one. You cannot not satisfy collision, but maybe you can let go of some fuel efficiency if you have to. And that's what we want out of this. We want to have gracefully degrading performance guarantees. Performance in this case means how many of the constraints you are okay with letting go, just to say that you can still finish your mission. Basically why? Because underwater, making it back home is probably worth losing one of your fins for it. You want the vehicle, and maybe one fin is a good enough sacrifice to still make it back. And this is a example of using only one of the methods, either only control barrier functions or only a behavior tree. On the top left, the constraints are basically don't touch anything. The orange line, the curve, is the trajectory of the robot, and the blue circles are hard obstacles, and the light blue circle is like a soft obstacle, as in it's just a distance we want to keep from that particular obstacle, but it is not a fatal obstacle, so to say. There's nothing to crash into, but the dark blues are solid rock, let's say. With control barrier functions, we can satisfy all of these constraints, no problem. It will go around all of the obstacles towards the goal, but it cannot reach it, because it is, in this particular state, impossible to reach it while keeping all of the constraints satisfied. It is just simply too far. The vehicle doesn't have enough battery for it. Whereas on the behavior tree side, it will still do all of the things it's supposed to do, which is satisfying all of the constraints, but it's a switching system. So it can switch between evade obstacle and go towards goal actions indefinitely, called chattering, and basically get stuck at the first obstacle and not go around it. Because the behavior tree at this point has no action saying go around the obstacle. It just tries to go, it sees the obstacle and tries to get back from the obstacle. It says, oh, I'm out of the obstacle, I can go now. So it just goes back and forth. Again, smooth constraints on a switching system like that is hard. So that's why we want to combine these things. When we combine them, what we get is basically what is on the bottom right figure. The behavior tree allows the control barrier function set. I won't go into details. We can go into details if you're curious about it. It can allow the control barrier function set to pick and choose which constraints to satisfy and when to satisfy them with a given priority order, basically. The structure of the tree determines the order in which you are okay with not satisfying some of the constraints. For example, this tree here is shown on the top right. You have no imminent collisions, that's prior to number 1 on the left. Feel okay is prior to number 2, and prefer safety margin is okay is prior to number 3. So the moment feel okay starts becoming a possible problem, the tree can just switch off the safety margin condition and just give up on satisfying that condition, and just to keep fuel, which is a higher order condition, satisfied. And that's what you get out of the combined system. You can see that the trajectory is basically the same until a point, in same as the control barrier function one from before. But at that point, the feel okay condition is unsatisfied. The behavior has realized, oh, I'm not going to make it with the feel I have if I satisfy all of the constraints. So it just switches off the safety margins and says, okay, cut through the safety margin. We need to finish the mission at that cost. But still, the hard constraint of collisions, avoiding collisions, is satisfied because that is a higher level constraint than fuel. But by giving up the safety margin, it saves some distance traveled, so it can still make it to the end of the mission, which is exactly what we wanted. We had just one condition being given up at only one point, well, after a point, and that has allowed us to finish the mission. And we can add planning to it. We can make it even more complicated by adding like charging, connectivity requirements, and so on. Let's see if this video works. I don't know what error 5 means. If anyone knows, that would be great. But I have trajectories for that as well. If I can move forward, there we go. So the initial configuration of a setup could be like you have 3 agents with different colors. And the conditions are that we want them to stay connected to at least one other agent at all times. That's one condition. And we want them to avoid collisions with each other and with the environment. Again, the blue circles. And we want them to stay charged at all times. We don't want them to run out of battery, obviously. And this is a coverage mission. You have they have some waypoints around this area going up and down. And you can see that at first agent, the pink one, starts with low battery for some reason. So that's the initial state. At that point, it can decide to just go back to the charging station, leave the other 2 behind. Because the battery constraint is basically the second highest constraint after collision avoidance, it gives up connectivity and it gives up the mission itself to keep the battery level charged. But the other 2, they have enough battery. They do the collision avoidance. You can see the orange guy just moved around the obstacle, and they have one body that they're connected to. So they can continue their mission. As they continue, the pink one is charged. It goes back to rendezvous with the other ones, because at this point it is charged, so all the other constraints can be satisfied, and one of them is to be connected to someone. But since the other 2 have gone on a long mission, they now need to go back for battery charging. So they give up. Purple and orange has given up on connectivity constraints, but the pink has not, because the pink is completely charged. It is trying to do the mission, but it is also trying to stay connected to some other agent. So it's basically dragged back to the charging station with one of the recharging AUVs, just to be connected to someone. Now pink is keeping the connectivity, while the others have given up on connectivity because they're recharging. And once they both charge, they continue their mission. They do all of their collision avoidance and so on. But at some point, pink is out of charge again because it had to go back, basically waste a bunch of battery going back with the other guys, and then has to go back charge and then come back for rendezvous again, finishing the mission. So this shows that we can switch between multiple constraints at any time using multiple agents, and this keeps all of the constraints that we want to keep still satisfied until some worse constraint is unsatisfied, at which point we can give them up. So the result is that it's a general purpose reactive control system that can satisfy multiple goals, as we have seen. Constraints were like collision avoidance, connectivity, complete your mission. We have gracefully degrading performance guarantee. We only go from the lowest priority conditions to highest priority conditions as required, basically, and this is designable by persons. In the worst case, if all of the conditions are unsatisfiable, it acts as a normal behavior tree with all of its known characteristics. Like that's the worst it can get, which is still very good. And we can incorporate planning into the whole system. We can say, oh, I cannot satisfy any of my constraints. Maybe I should make a new plan. That itself can be a constraint. So it can get higher level than what we have shown here. So that was combining control barrier functions with behavior trees. And now going back to the big picture where we need to cover a lot of area, a lot of volume with multiple agents. And that's where efficient navigation-aware surface coverage using AUVs comes in. We need to know how we can guarantee the coverage that we do, even with one agent. Before we can guarantee we can cover an area with multiple, we again need to do it with one. We need to know just how efficient different approaches can be, what their limits are, what characteristics they have. If we can know these, then we can plan for multiple agents, because all of these are basically interfacing points between all of these agents. If I don't know where you are, I cannot predict where I should be if we're a pair, basically. So if I know what you're doing, if I know your guarantees, I can make a plan around your guarantees so that to put together, we can guarantee a bigger mission. And this is basically what we have. Navigation inaccuracy is the biggest problem when you're underwater. There is usually not much to correct your localization because it's usually just flat. Going up for GPS is what we assume we don't do in this case because it's very costly to do so. It takes a lot of power to do it, going up and down all the time. Plus, even if you do go up and down, the moment you start going down, you start losing your accuracy immediately. So whatever you do, the AUVs are inaccurate to some degree. But this is a measurable inaccuracy. We kind of sort of know how inaccurate they can be at the worst case, and that's we can compensate for. So that even if the worst case scenario happens where the AUV gets dragged hundreds of meters, if we know how much it's going to get dragged, we can make a mission such that under those circumstances, we can still know exactly where it can cover. And these are such examples. The green dashed dot line is the plan, and the red is the actual trajectory of the AUV. On the right one, the AUV is drifting towards the left because there's a current, it's drifting there. In the bottom one, it's drifting towards down. But either way, the black rectangle, which is the coverage area that we wanted to cover, is covered, even when the AUV is incapable of completely doing the mission that we gave out. Because the mission knew, oh, it is possible that the AUV might get dragged. So it has all of these margins saying, oh, if you get dragged to the right, I'm going to put some margins to the left. So even if you do get dragged, you will still cover the area. And then this, of course, has efficiency questions. When you add so much buffer areas to basically everywhere, how bad does your efficiency get? And in this case, we define efficiency as total work done, as in total distance traveled over the actual area that you covered. So the less distance, the more efficient, the more area, the more efficient, basically. And there are basically two ways of doing this. You can either do this rectangular pattern, which is what I have shown, or you can do a circular pattern, which is very similar. Instead of doing rows like this, you do a flower shape going back and forth from the same location. It has different efficiency characteristics because there's a lot of overlap in the center and almost no overlap at the edges of the circle when you do a flower shape like that. So we wanted to compare them, like which one is better. It turns out they are better at different settings, basically. In the bottom right, you see K is how quickly the localization gets bad. The exact metric of it is not important right now. But you can see that there are times when the circular one is more efficient and where there are times when the rectangular coverage is more efficient. So there is no one answer to, you should always do this. It depends on how big of an area you want to cover, how bad is your localization inaccuracy. And even for the rectangular area itself, it matters if you do a long and narrow mission versus a wide and short mission. That's what you see in the bottom figure. The lighter the color, the more efficient it is, and it's the X and Y sizes of the area you want to cover. Basically, pick the lightest area that is closest to the area you want to cover, and that's the most efficient way of covering it. That every pixel is effectively a setting for the coverage area. So that's what we found out. Now, what am I doing nowadays? I'll come to that. Now that we know the efficiency characteristics and what kinds of shapes and guarantees we can get from one AUV, we can use this for multiple AUVs and we can add to this the fact that they're now cooperating, which is exactly what we wanted to do. as I said, SLAM underwater is very hard. If we had our SLAM people here, I think they would be nodding their heads. So in the end, we want to make plans that increases localization accuracy using each other as ways to do SLAM. It handles interferences because your sensors and ranging equipment and communication equipment all usually use acoustics. They all interfere with each other. Your existence there is an interference for some other agents to communicate. That's a huge hassle. And we want to increase total coverable area. We want to have guarantees of we can definitely cover this with this many AUVs with this much time. If we don't do these, if we don't do what I am trying to do, this is kinds of the results we can get out of multiple AUVs trying to cover an area using a rectangular pattern. The moment they get an inaccuracy in their localization because maybe they saw a rock, or they thought they saw the same rock, but it is not the same rock. That's the right-hand figure, basically. They can localize with that rock in mind, but if it is inaccurate, then you basically throw out the entire future mission because your route of your localization is incorrect. You localize on something that is not there. So you might think you're covering it perfectly, but your AUVs are all over the place. And if there are drifts and currents in the water, what you get is basically the bottom picture. The dashed lines are the plan, and the solid lines are basically what actually happened. So there's clearly a current to the right. So the AUVs going to the right have gone overshot. There's a bunch of holes in their coverage, but all of these problems are unknown because they haven't been corrected. That's what we want to. That's what I want to do with this, with my current project, where I want to do cooperative localization. If these AUVs can speak to each other in the middle of their mission, they can realize, especially in the case that the right one happens. I think I did a rectangular shape, but it cannot be. We can use this information if they can range each other, if they can measure each other's relative locations and communicate some shortened version of their trajectories. This can be acquired using pose graphs. This is exactly what I'm doing. Somehow merge them, optimize the collective graph, then they can correct each other during the mission so that neither of these happen, basically. That's what I'm trying to do. And this, even if they are overshooting or undershooting their plan, now they know they're overshooting or undershooting, and that itself is valuable. Now you know where your holes in your coverage are, or where you haven't covered at all. So you can still say the coverage is good, but we know we have holes, and we know exactly where those holes are. It's not like, oh, we think we covered everything, but there are in reality holes that we don't know about. That's the worst case scenario in coverage, that you have holes you don't know about. And that's this project is trying to solve, that we learn where the holes are. And that's what I've been doing. Thank you for listening. I think I'm a little over time, but thank you for your patience.